Planes. A plane is an infinite structure that is parallel to two position vectors B and C. So that's these ones here. So infinite means it goes on forever. Goes on forever. I've drawn it as a red box here just to get the point that it's flat, just to get the point across that it's a flat thing, but actually it has no boundaries. It keeps going forever in all directions, but it is flat. So it's a big flat thing that's parallel to these two vectors B and C, which have the directions shown. Now these two vectors B and C originate at the point P, which is also inside the plane. So the plane, this big infinite structure, this big flat infinite structure in 3 dimensions, goes through the point P, and it is parallel to these two vectors. If you want another more simple example of a plane, it's horrible. Consider, so this is the z-axis, and let's say that this is the x-axis, and then I drew the y-axis in this direction, but it doesn't really matter. So let's say this is the y-axis. Consider the xy plane. It's a bit better. Alright, so this is the xy plane here. The xy plane. It's completely flat, which means it only has 2 dimensions. In fact, let me write that word out. So 2 dimensions. And here, dimensions refers to the fact that it is parallel to 2 vectors. And those 2 vectors, in fact, you can choose any 2 vectors contained within the xy plane that are not parallel to each other. I'm just going to take the vector 0, 1 and the vector 1, 0. So it is 2-dimensional. That means it's parallel to 2 vectors that are not collinear or in a straight line. So parallel to 1, 0 and 0, 1. Just make this word a bit clearer. Parallel to exactly 2 vectors that are not multiples of each other. And also these 2 vectors 0, 1 and 1, 0 originate, we can say that they originate at our point P, which is the origin, originate at 0, 0, 0. So that's a simple case of a plane. It's 2-dimensional, which means it's flat, but it is contained within R3, or 3-dimensional space, 3D space. Okay? And it goes on forever in all directions, obviously, but I've had to draw it as a box here just to get the point across that it's flat, but in reality it keeps going along here. So it keeps going forever in that direction, and it keeps going forever in that direction, and also in this direction, and in that direction. So that's a very simple case of a plane, but they don't all have to look like that. In general, they look just something like this. They don't have to go through the origin, and they can be on any weird angle that we want. By the way, I might have done something confusing by calling these vectors 1, 0 and 0, 1 when we are in 3-dimensional space. Remember, 3-dimensional space is the set of all points, well, let's say, or vectors let's say points with position vectors x, y, z, where x, y, and z are real numbers. So this might have been a little bit confusing, so let me change that. So instead of just 0, 1, what I really meant to say was 0, 1, 0. And similarly, instead of 1, 0 here, what I really meant to say was 1, 0, 0. Notice, however, that for all of the points in our xy plane, the z coordinate is 0, and that's because we don't have a z coordinate, which is why I wrote my vectors like this in the first place. Kind of forgot about the z coordinate because it doesn't exist in this. Well, it's 0 in this plane. So note that we can write our xy plane as follows. We can call it just x, y, 0, such that x and y are real numbers. Or another way to write it, if you like, we can say x times 1, 0, 0 plus y times 0, 1, 0 for x and y that are real numbers. More generally, we can write it like this: 0, 0, 0 plus x times 1, 0, 0 plus y times 0, 1, 0, such that x and y are real numbers. And what that means is we can get to any point in this plane that we like. Just bring that up a bit. We can get to any point in this plane that we like by starting at 0, 0, 0. So we start here, and then we can go any distance we like along this 1, 0, 0 vector. So along here, for example, we can go to this value here, x, and then we can go any distance we like parallel to this 0, 1, 0 vector over here. So that would be a distance of y. So we can get to this point here that clearly has coordinates x, y, 0. So we've written it as the combination of an initial vector, so I guess we can call it initial. So this vector here gets us onto the plane, and then we can go some distance times one of the vectors that the plane is parallel to, and another distance times the other vector that the plane is parallel to, and that allows us access to any point on the plane that we like. Taking a look at the more general case of this plane, if we, so this plane is just some arbitrary plane now, but if we start out at the origin, and then so the vector equation of the general plane is p, so that would be this vector here, this green vector. Let me write it in green. So if we go along this p vector from the origin to the point P, then that gets us onto the plane. And then once we're onto the plane, we can access all the other points in the plane by going some multiple of this b vector and some multiple of this c vector. For example, suppose I want to get over to this point here in the plane. Well, clearly I'm going to have to go some negative multiple of b, which, to be honest, looks about negative b. So let's say negative b. And then I'm going to have to go some multiple of c, probably about half of c. So let's say 1/2 of c. And you can do the same kind of thing to get to any other point that you like. For example, to get to, say, this point here, it's clearly going to be about 1/2 of B plus 1/2 of C. So this point here, let's call it W. So let's say the vector from O to W is equal to OP, which is the P vector, plus 1/2 of the B vector plus 1/2 of the C vector. And so taking this equation, R of the variables or parameters T and S, and allowing all T and S in the real numbers, so allowing them to vary, we get an infinite set of vectors that go from the origin to a point on the plane. For example, over here the vector OW equals P plus 1/2 B plus 1/2 C. So we will have OW is the vector from the point O to some point W on the plane, and that's just equal to R of 1/2 and 1/2. So we call this thing the vector equation of the plane. It gives an infinite set of vectors that go from the origin to every arbitrary point on the plane that we like. And if we call the vector B, we let that one be B1, B2, B3, so some arbitrary vector in R3, and C equals C1, C2, C3, then this is the equation of R equals P plus TB plus SC, written out in full here, just using those coordinates and addition of vectors and scalar multiplication of vectors.